Okay, so in this slide, we are going to work on rimless wheels, equations of motion, and its solution to demonstrate the passive walker. The ordinary wheel looks like this, the full complete rim and the spokes. And then if I sort of make a hole between the rims, so it's kind of synthetic wheel, looks like this. So it'll like a human center of mass and maybe a massless leg kind of type with the foot, curvy foot. So if I just eliminate those rim completely, that's a rimless wheel. So if you can imagine how this spoked system coming down the slope is like, one by one kind of stepping down. So this could be a good example working on the passive walker, the simple model for the passive walker. So to describe the motion of the center of mass, I'm going to define the angle theta with respect to this inclined vertical. The theta is a counterclockwise positive, and the spokes has a finite defined spoke angle, which is 2 alpha, and all the spoke parameter, the mass parameters are given like this. To generate the equations of motion for rimless wheel, there is only one contact here with the ground, so there is going to be x components of the force and y component of the forces in the gravity. And you know that the direction of the total x and y direction of force at the contact will be aligning with the leg if the leg is massless. We talked about it in the previous section because for net sum of the moment to the massless leg should be 0, so the force should be aligned with it. Okay, so the basic equations of motion for this configuration is going to be maybe the torques applied with respect to the point O is going to be IO and theta double dot. And the torques applied here is only by the gravity, so the L vector from O to center of mass, cross product mg is going to be generating the torques that has I theta double dot. So to calculate this cross product, let's just zoom in the angles for the gravity, which is perpendicular to the Earth horizontal, and the spokes has an angle with respect to the slope perpendicular. So the total angle between the leg and the gravity is gamma plus theta. So it's going to be MGL sine gamma plus theta plus gamma, which is going to be I theta double dot. And for assuming small angle, it's going to be MGL theta plus gamma equals to IO theta double dot. So if you rearrange them, this is a simple inverted pendulum model equations of motion with forcing function. Here, the gravity takes a role for the forcing external force. And IO, if this is a point mass, it's going to be simply ml square. And if it is something like a rigid body kind of thing, then you should also add I of that rigid body with respect to the center of mass. And let's assume that's expressed by mz squared, the z as a radius of gyration. So your equations of motion will look like theta double dot and minus theta and the external force. And if you have a normalized ratio of the radius of gyration with respect to leg length, and then set the parameter pretty simple, like L equals to 1 and G equals to 1, then simply your equations of motion for the inverted pendulum is going to be theta double dot minus sigma square theta. Sigma is here, and gamma term, the external force term. So that's the equations of motion of this rimless wheel when the spoke has a rotation, okay, initial rotation. So let's find the solution for that single support phase of the rimless wheel. So since the equations of motion is given, we are going to start solving it with the defining initial condition. So initial condition, let's assume starting the equations of motion with this initial contact of the new stance leg, stance spoke with the ground here. So initial angle, this one is going to be half of the interleg angle, which is 2 alpha. So this is going to be minus alpha here. And let's assume the counterclockwise angular velocity is given as initial value. So the initial condition is given like this. If you look at this, this is a second order differential equation with the excitation. So you will have homogeneous solutions and particular solution, and it's a summation as a total solution. So homogeneous solution means there is no input here. So you can assume typical exponential function as a solution. And if you plug that into this homogeneous differential equation, what you can get is s squared minus sigma squared. Turns out to be 0. So you can find what's going to be the exponent for this homogeneous solution. So what you can have is a homogeneous solution is expressed by unknown coefficient a1 and unknown coefficient a2 with the function of e to the sigma t and e to the minus sigma t. And also for the particular solution, since it has a constant input, your particular solution for the theta is going to be a constant value minus gamma here. So your total solution is going to be summation of a homogeneous solution and the particular solution, and those two unknowns for the coefficients will be found from initial conditions. So if you plug into these original equations of motion and just apply the initial condition, you can specify a1 and a2 and try by yourself, and you're supposed to have this one as a solution. So you have some coefficients for the exponential sigma t with the gamma as a function of gamma, omega naught, and sigma and alpha, all those initial conditions and model parameters, and also some coefficients about gamma and initial conditions for e to the minus sigma t and minus gamma. How do you expect this function will look like? Okay, so this one has exponential increase, and this one has exponential decrease with the minus minus exponent. So if you sum them up, your theta will look like just a monotonic increase starting from minus alpha here up to the alpha right before collision. And this does make sense because if this is rotating, the Rimless wheel is rotating, maybe this angle is getting smaller and going to the upright, perpendicular to the slope, and just falling forward. So it's pretty much a reasonable solution. Okay, so this actually solutions and equations of motion holds up to the single support phase. What I mean by the single support phase is before the collision occurs. So here, this leg, this spoke is going to be coming down as this total system rotates, and it'll actually hit the ground and become a new stance leg. So this we can solve up to the collision part, and whenever there's a collision occurs, what should it do? Recall that your dynamics course, what you learned in undergrads, when the collision occurs, suppose that you have a MV minus is hitting the capital M, which is stationary. What will happen is you can actually apply the Newton's law, F equals ma, and you took the time integral on both sides. And as far as there's no external forces, like if I assume this one is a total system, there's no external forces applied, then your momentum change will be conserved. So your initial linear momentum will be equal to the linear momentum for after collision. So that's what we used for the collision equation. So similarly, to analyze this collision for the Rimless wheel, I'm going to draw the F equals ma form initially. So initially, it has a velocity perpendicular to the previous stance leg here, right? So this is going to be mv minus, and how we can figure that out? Oh, you can just solve the equations of motion, what we just worked on in the previous slides, up to the point where your next spoke is about to hit the ground. Okay, so this one could be solvable. And this one, right after collision, we want to know what's going to be the right after collision velocity. Okay, so to do so, we are going to use this momentum equations. So this one is now perpendicular to the new stance leg contact with the point C. And the forces applied during those collision is going to be the contact force from the point O and point C and the gravity. And note that whenever there's a collision occurs, there is a very large amount of force applied for a very short amount of time. That's what we call the impulsive force applied at the point C. Okay. So if I applied impulse momentum relationship, I can obtain the equations of motion for that, F equals ma here at this configuration. And if I do the time integral between right before collision, right after collision, I might figure that out what's going to be the after collision velocity v plus. However, when I'm calculating this part, since this FC is very, very large, so integrating over time with a very short amount of time, it's not negligible. And then usually, generally, those impulsive forces is unknown. So even though I can obtain the equation, but there are two unknowns. Left-hand side, I don't know what's going to be the linear impulse applied by the FC, and I don't know what's going to be the V plus after collision. So this equation is not helpful. So what should I do? Think about it. For the Newton's law, you can also multiply by the moment arm cross product on both sides and take the time integral to obtain the angular impulse momentum relationship, right? So that's going to be the change for your angular momentum relationship, which is by definition R cross product mv, moment of momentum, okay? And then this can be also expressed by the I omega. And note that here, your moment arm could be defined from some reference point. So depending on where you set the reference point, those are the subscript should be applied here, okay? And here. And note that this V is usually defined in an absolute coordinate frame. But anyway, so instead of applying the linear impulse momentum relationship, let's apply angular linear momentum relationship. And we should set which point should we set as a reference point to define the angular momentum. And there could be three options for this case, like O, one contact point for the ground, with the ground, and the other contact point with the ground in the center of mass. Okay, so if we set the reference point of the angular momentum definition as O, then we should calculate the angular impulse with respect to the O. So that includes the angular impulse by the FC, which is unknown. So point O may not be a good candidate because even though we apply the angular impulse momentum relationship, there should be unknown on the left-hand side and unknown for the right-hand side. How about point G, the center of mass point here? Well, the angular impulse by this force and by this impulsive force is going to be 0 because there is no moment arm. But also the angular momentum, the moment of momentum, R cross mv is also 0 because it's at the center of mass. So it's kind of trivial, like you will have a 0 equals to 0 kind of stuff. So finally, maybe we should apply the angular impulse momentum relationship with respect to the point C. This is new ground contact point here. Okay, so let's work on it. So starting from F equals ma, the Newton's law, Newton's equation, the moment equations of motion. And there are three forces, Fc, Fo, and mg. And I'm going to do the R cross product from the C on both sides, and we'll take the time integral over t. Okay, compared to, and then that's going to be result in the angular momentum change for the before and after collision, and that includes the V plus term. That's what we are going to figure that out. Okay, for these two forces are compared to this impulsive force Fc, it's very, very small. So time integral over a very short amount of time from, collision before, collision after, from minus to plus, it's going to be really, really small. So the impulse by the gravity and Fo could be negligible. And for this one, even though this Fc is going to be really large and cannot be ignored over the integral, but this moment arm, okay, RC is going to be 0 because Fc is applied at C, okay? So this term also turns out to be 0. Therefore, there's no angular impulse applied to the system, so before and after, your angular momentum is conserved. So this one will be conserved, okay? So let's figure that out, what's going to be the before and after angular momentum. To figure that out, let's just specify the angles here. So at the ground contact point, you have a interlag angle 2 alpha divided by the 2. So this one is alpha. This angle is alpha. And the angle between MV minus and MV plus is going to be 2 alpha. and parallel to the Earth horizontal, this is going to be alpha. So using those configuration, you can figure that out. RC cross product MV minus and RC cross product MV plus, which is, so it should be minus like a plot later after collision minus before collision. So this should be changed. Okay, anyway, so the before collision, the angular momentum is going to be ML sine 90 degrees plus 2 alpha. Okay, so you have a angle cross product between this L vector, and this MV minus vector, so this angle. Okay, and minus MLV plus. Since this L and V plus vectors are perpendicular, so you can simply just multiply by the value. So if we can rewrite it as a cosine 2 alpha, V minus, and if you have a V minus and V plus can be expressed by the omega, which is L cross product omega. So here it's going to be L minus, omega minus, and it's all L omega plus. What you can have is your omega plus is going to be expressed by omega minus cosine 2 alpha from angular momentum conservation. So as you can see, after collision, your angular velocity will be decreased by the factor of cosine 2 alpha, which is less than 1. Okay, so for the case where you have a rigid body, like a torso, okay, so this is not point mass anymore, what should you do? For the rigid body, you can establish the Newton's law from Fi to the particle I is going to be same as Mi Vi time derivative, and you can do the sigma to integrate all the particles that constitutes a rigid body. So you are doing the R cross product both left and right hand side, and if you take the time integral, that's the angular impulse momentum relationship for the rigid body. Okay, so for the R, since we are defining the set the reference point for the angular momentum with respect to the C, those Ri vector is going to be composed by this L vector plus rho I. Rho I is the distance vector from center of gravity to a specific particle I. And for the velocity, it's going to be split it out as a center of mass velocity and its particle velocity, okay, with respect to the center of mass. So if you expand this to parentheses cross product, you can have a L cross product MV, rho I cross product MIV bar, and L cross product MIVI, and rho I cross product MIVI. Okay, here, those V bar and L is going to be coming out of the sigma, so you will have a L total M. And here you have a rho I Mi multiplication over the sigma, and you have a Mi Vi multiplication over the sigma, and that turns out to be 0 due to the definition of center of mass. So what you can have is the very first term and the very last term, which is L cross product MV bar, and it's gonna be since this Vi is gonna be expressed by rho I omega, you will have a rho I square Mi omega term. So this is what the moment of inertia term here. So you will have L cross product L cross omega, and this one has been added compared to the point mass derivation. So if you are going to solve the collision equation for the rigid body rimless wheel, then you will have additional, in terms of L cross product MV term, you will have additional mz square omega minus mz square omega plus. So if you just just rewrite the equations, and if you if you solve everything in terms of omega plus, instead of omega minus cosine alpha, you will also have a parameter that includes about the shape of your rigid body, mass distribution of your rigid body. So if I set it this coefficient as an eta, okay, as an eta, as you can see here, eta is less than 1. You will have omega minus multiplied by the eta, which is equal and less than the omega minus. So what that means is after collision, your speed will reduce, for certain, of course, because there is a collision energy loss. So V omega plus will never greater than omega minus, and this is the equation after collision. So if I recall the solution steps for solving walking model, we have a two-stage. The very first stage is the solving the single support phase, where this light blue leg is rotating forward. Okay, so obtain the equations of motion for the stand phase, which is just a simple inverted pendulum with the gravity external force source in this setup. And you can have a complete analytical form of theta and omega. So you can solve this up to the point where the collision occurs. And during the collision, at impact occurs, you should apply angular impulse momentum relationship and can figure that out. What's going to be the relationship for this before collision and after collision relationship for the theta and omega. Theta is a simple swap with the minus sign. And for the omega plus, by applying the angular impulse momentum, you can have a multiplication for the eta components for the before collision omega minus. So by having that, you will have a new stance leg here. It's like a blue leg. So with the initial condition as omega minus and omega, initial condition of angle as minus alpha and initial condition for the angular velocity as omega plus, you will have, okay, right here, you will have another equations of motion for the single support phase to solve. So you just keep repeating solving this until you figure that out, maybe finding the periodic gates or behavior for the repeated gates. Okay, so to have a steady state gate, which means you are keep having same sort of repeating the same state variable set for each single stance. That means your omega plus here turns out to be same as initial omega naught here. So this one should be same as this one. So this is going to be the condition that maintains the steady walking. Okay, so since you are going to lose some velocity components due to collision, omega 1 should be a lot greater than omega naught throughout those forward rotation or forward movement during the single support phase, and those energy has been provided by the gravity here. Okay. Since this rimless wheel simulation or scheme is very, very famous, there are many good resources you can find for the web. If you type in a rimless wheel, either simulation or the MATLAB code, there are many good samples. So this is a typical rimless simulation going downward, and there is a site that you can actually adjust the model parameters so that you can examine how your change for the parameter will affect the solution for the rimless wheel.